Okay, great. So great to see you guys. We've been hearing a lot so far today about computers and AI and how they work and how to make them work better. We've also been hearing a lot about the societal implications of that, what does it mean for education, for national regulations, et cetera. What we're going to do in this panel is talk about humans and AI working together. So that will be the key focus of our panel. And I will begin by talking about some of the research we've been doing as part of the T6 project. We'll have Hamza talking about her research, and then we'll have a panel discussion following that. So what I want to talk about for my research presentation is how to design human AI superminds. Now, what do I mean by supermind? My definition of superminds is groups of individuals working together in ways that seem intelligent. Now, that's a very broad definition. By that definition, superminds are all around us all the time. Every company, every hierarchical company you've ever heard about is a kind of supermind, a group of people working together in ways that at least sometimes seem intelligent. So is every democracy a supermind, whether it's in a club or a company or some other kind of group. Every market, whether it's for cars or currency or whatever, every market is a kind of supermind. Every community is a supermind, whether it's a scientific community like the one shown here, a neighborhood, or the community of people in this room right now. All of these are superminds. One thing you realize when you look at these superminds is that computers are also often an important part of superminds, and they can sometimes make these superminds much smarter. But there's still a lot of things we don't know about how to create human-computer superminds. One of our goals in our research project is to come up with a kind of scientific foundation for how to design human AI superminds. One of the things that would be very helpful in a scientific foundation for that is to be able to predict the performance of human-computer superminds. So I want to give you now a simple example of that. In preparation for this talk, I thought it'd be kind of cool to demonstrate this, a simple supermind, involving creating an image of what this room was going to look like today. So I actually spoke in this room in January, so I knew pretty much what it looked like, but I wanted to see if I could get a generative AI system to generate an image, okay? So I gave it the instruction, this is ChatGPT 4.0 for Omni. Please create a picture of the MIT Singapore AI Symposium 2024, which was organized, et cetera. So I thought that was a sensible prompt. So here's the picture I got. What do you think? Does that look like this room? Not exactly. Much bigger, multiple floors, et cetera, et cetera. So I said, please show the attendees at this event in an auditorium listening to a speaker. That should look more like us, right? Here's what I got. Close, close. They even got something kind of like the MIT logo at the left in the front. The chairs are the same color. Amazing. But it's got that big balcony stuff, so I said I didn't like that. So I tried again and I said, please keep the picture the same, but remove the balcony. And here's what I got. I think that's pretty close, don't you? I'm going to declare that success. So that's a simple example, but it turns out that's an example of a very pervasive process. It's what you could call a human-computer hierarchy with the human as supervisor. So I was the human, the computer was the worker. The process was human gives directions, computer generates some output, human judges whether the quality of the output is good enough. If it is, if it's not, repeat, otherwise stop. So very pervasive process. That's something almost many people use when they're using ChatGPT or other kinds of generative AI. Very pervasive for many kinds of tasks. It turns out that it's not hard to create some simple equations to predict the performance of this process. I won't go through the details of the mathematical equations. It has parameters for things like the cost of generating an image or generating an output and the cost of judging and so forth. What I will tell you what the equations say in English. Basically, they say there are three conditions needed for that human-computer process to be better than either the human alone or the computer alone. We'll assume those are the two alternatives. So in English, there are three conditions for that. The first is the computer needs to be able to predict or to produce the output much more cheaply than the human. That's not too hard, because if a computer can do it at all, it's usually way cheaper. The second condition is the human can easily tell whether the output is acceptable. That was certainly true in this case. Just by looking at the picture, we could instantly tell whether it's good enough. In other things like generating software code, it might take you as much time to figure out whether the code is correct as it would to just write it yourself. So that condition is not always true. The third condition is that many of the computer outputs are acceptable, but not enough to rely on the computer alone. If it was enough to rely on the computer alone, you wouldn't need the human. And if hardly any of them are acceptable, it wouldn't be worth using the computer. So if all three of those conditions are true, this is a good process to use. So that's an example of a quantitative evaluation that can be applied to many different processes. That's an important part, I think, of a science of designing human-computer superminds or human AI superminds. One thing we want to do in our research is develop more and more of those equations. And I think the point here is that it's very general, too. So another thing you'd like to have in a scientific foundation for generating and designing human-computer superminds would be a way of identifying possible designs. We've already talked about how to evaluate a design. How can you generate possible designs for a human-computer supermind? We developed a methodology we call supermind design. It's kind of loosely analogous to something like design thinking, but focused specifically on designing superminds, especially including humans and computers. We've also, perhaps even more interestingly for this group, developed a system we call Supermind Ideator, which essentially, it's built on top of GPT-4. It essentially uses the LLM to do the moves that we advocated for humans using our design methodology. So it essentially automates that design methodology. The way it works is you type in a problem at the upper left, anything you want in English. Then the system uses those moves to generate a bunch of ideas that may be relevant to your problem. It turns out that, I talked about this a little bit in our January meeting. Since then, we've evaluated the use of this system. We found that when we had humans judge the quality of ideas generated by the humans using this tool, they judged that the human ideator combination generated ideas that were significantly more innovative than humans using ChatGPT, and that in turn was significantly more innovative than humans working without either of these tools. So we think that's good validation for the approach. We think, however, that it's possible to do much better than we're doing so far with prompted and fine-tuned LLM. We think it's possible to have an explicit model of the possible ways of organizing groups of humans and computers to perform different kinds of tasks. So we think one way of doing that is to create a kind of ontology of human-computer groups, and in fact of many kinds of groups. The idea is that we think that can be done in part by having a taxonomy of different types of tasks. By analogy, this would be equivalent to the taxonomy of different types of living things on our planet. Biologists talk about animals and plants, and animals are mammals, birds, etc. We think it's possible to do something similar with activities. So we think that, I'm sorry, let me say one more thing about the living thing taxonomy. as in object-oriented programming, if something is true at one level, it's true of all the things to the right of it in this diagram, all the specializations of it, unless that's specifically overridden. So with animals, they eat other things, other living things. Birds do that, and they also have wings. Waterfowl have both those things and others, et cetera. So we think it's possible to do something. I'm going to go longer than that, okay? We think it's possible to do something similar to that with activities. We think that's a not appreciated, not recognized possibility that has potential to be very powerful kind of science. So, for instance, this is a tentative version of what such an ontology or taxonomy might look like, a kind of family tree. At the left, it talks about act, the most general kind of activity at all. Then there's a level of slightly more specialized, but still very general activities. So create, decide, sense, remember, those are all very general types of activities, kind of like plants and animals in the other one. Each of those can be further specialized to a great level of detail. Like on the far right, you have things like deciding, a shoe leather worker deciding what materials to use. So, and again, at each level, something true at one level is inherited by all the levels to the right of it, unless specifically overridden. In this case, it's just what are the inputs and outputs, but it could be all kinds of things. And importantly, at one level, it goes all the way to the very detailed things that you don't have to think about specifically. It's just automatically inherited. Interestingly, the equations that we talked about at the beginning apply to essentially all activities. So those are things that are relevant to almost any kind of activity. So that's a great power, we think, in using this approach. Another question is, how can these approaches be applied? We've worked with several organizations to apply some of these ideas. For instance, we studied procurement at a ship management company. We came up with very detailed maps of the processes they use. And then we put those in the context of this more general ontology of activities, starting with act and the first level after that. Then we got to buy, and it shows here the sub-activities of buying in general. And then we show how the process of buying at this organization is a special case of that inherits some of the things and specializes others to a greater degree. We think that's useful for mapping, using the structure to map things. It also turns out that it may be very useful for managing knowledge about these different kinds of activities. So that's one way of using this. Another example that we looked at is an airport, and looking at the airplane turnaround in an airport. Here's a high-level version of our map of that. We also situated this in the context of the more general family tree of types of activities, with things like managing transportation vehicles at the left, and then to the right, various kinds of turning around an airplane at an airport. In this case, we used the taxonomy or the family tree to get new ideas for how this process might be done. So you can think of that as looking at the ancestors, the aunts, uncles, and cousins of the place you started. Here's a list of ideas we came up with by doing that. My favorite one on this list is the one highlighted in orange there. It's about the crew of a Formula One racing crew. So here's a video of that. It shows how they are able to have 22 people change 4 tires in 2.5 seconds. You can look at that again if you want. But the idea is there might be some ideas from that could help you think of new ways of doing a rapid turnaround for an airplane at an airport. And that's just, of course, scratching the surface of the kinds of connections that this might help you make. So, what are the possible uses of these family trees? They can help you generate possible designs. One we're particularly interested in is identifying possible uses of AI, generating improvements for existing processes, creating detailed process designs for new processes. It could help in the kind of runtime management of processes, helping you improvise when something unusual happens. And as I said, it could be used to help manage knowledge according to the activities it's relevant for. So, the two key conclusions to leave you with: the approach we're using has the potential to help develop powerful new scientific theories and many useful practical applications. Thank you.
Now,